with all that in mind, let's just dig in and observe how overfitting comes about in the context of decision trees. When we start learning a decision tree, we learn a decision stump, which is a very simple boundary between the data. Let's say in our simple example we've been using, it's either a vertical line or a horizontal line. And so in this case, when the decision is with respect to x1 as to whether it's less than minus 0.07 or greater than minus 0.07, so if it's less than, we're going to predict minus 1, and that will correspond to this side of the decision boundary. But if it's greater than minus 0.07, we're going to predict plus 1, and we're going to be falling to the right side of that decision boundary. And so that's a very simple decision boundary with just a depth 1 decision tree or a decision stump. But as we increase the depth, that situation becomes more and more complex. The decision boundaries become more and more complex. So you can see, as you increase the depth, you increase the complexity of the decision boundaries, until we end up with a super crazy one here where the depth is 10. And so that depth 10 decision boundary has 0 training error. So the training error at this point goes down from 0.22, which is relatively high for decision stump, through 0.13 and 0.10, which are depth 2 and depth 3 decision trees, which looked okay, to this crazy decision tree of depth 10, which had 0 training error. And this should be a big warning sign for you. And I should start phase. We've seen that with decision trees, as we increase the depth, the training error goes down until we get to a point where training error can even reach 0. And very often actually does, in this case with decision tree of depth 10. So you could say, oh, decision tree of depth 10, that's great, it has 0 training error, so that's a perfect decision tree. But in reality, it's not a perfect decision tree. And as we know, even though the training error is 0, the true error can shoot up. And so this can be a really highly overfitting decision tree. So it's good to take a step back and really understand a little bit better why the training error of decision trees tend to go down so quickly with depth. So let's take this simple example where we're just learning decision stump. We had 40 data points, just like we've been using. 22 of them were safe loans, 18 were risky. And we chose first to split on credit. Now the question is, why did we choose to split on credit first? Why was that the first feature we chose? And the reason we choose to split on credit first is because it improved the training error the most. It improved the training error from 0.45 to 0.20. So that was a good first split to make. Now, if we go back and review the algorithm for choosing what the best decision split is, the best feature to split on is, we try every single possible feature and pick the one that decreases the training error the most. And so at every step of the way, we're adding features that decrease the training error. And we're adding features that decrease the training error. And we're adding features that decrease the training error. And eventually, we're going to drive the training error to 0. Unless, of course, we get to some points where we can't drive the training error down because we run out of features to split on, or we have positive points on top of negative points. But that's kind of a side note. Most importantly, just remember the training error tends to go down, 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 down. And so that going down as we increase the depth is what leads to this low training error, which often leads to these very complex trees which are very prone to overfitting. And here's a real-world data set from loan data where we actually observe that big bad overfitting problem. So if we take the depth of the tree and we push it all the way to depth 18, we'll see that the training error has gone down a lot. And it's the blue line, which gets you down to about 8% training error, which is extremely low. However, if you look at the validation set error, man, that was not so good. Maybe that's around 39%. And so there's a big gap between the two, which we will characterize as a form of overfitting. If somehow you were able to pick the best depth for a decision tree, which in this case was depth 7, then you notice that in this case, the validation error is just under 35%. In other words, if I could pick the right depth, I'll get 39% validation error, but if I let it go until very low training error, I get a validation error of 39%. So going all the way, bad idea. Gotta stop a little earlier.